Hello students, welcome to the PYQ discussions of the CBSE board examination for chapter 12, 2023 and 2024 question paper, linear programming. In this chapter, we know definitely this is a separate unit which comes for 5 marks, and most common pattern of question that comes in this chapter is 1 plus 1 plus 3. But in last few years, we have seen that there are few regions where it was just directly a 5-mark question, but don't worry, it was not difficult. It was a straightforward graphical solution for a linear programming problem, ideas. And also in one region, it was a 1-mark question for MCQ and a case study, and that also was a straightforward, very simple question. So they don't have anything complicated to ask from this chapter. You'll always get perfect 5 marks from this chapter. But the only thing that is, students are very careless about shading the correct feasible region for the problem. That is it you have to be very careful about. So please listen to the various techniques I'll be discussing in this chapter. So first I will start with the MCQs and the few 5-mark questions that came throughout the regions in 23 and 24, my dears. So let's start with the first question, my dears. Question number 1. So this is MCQ, my dears. So please read it. The corner points of the feasible region is given to you. So we know that a feasible region of an LPP obviously has a corner point, and our solution always exists at the corner points. So they're asking you which corner point gives me the maximum value, which corner point gives me the minimum value. You just got to put the corner point. Each corner point should be substituted in our objective function z is equal to 18x plus 9y. So 18 times 2, 36. 72 times 9, so 9 2s are 18, 63, 66, 48. So if you add it up, 8 plus 6, 14, and 8 and 684 is the first value of z corresponding to the corner point 272. And then next point is 15, 20. So 18 times 15, my dears. So 18 times 5 is 90, and 18. So your answer is 270. 270, and 20 times 9. 20 times 9 is 180. So it's going to be 0, 8 plus 7, 15, and that is going to be 450. Next corner point, my dears, is 40, 15. 18 times 4 is 720, okay, plus 15 times 9 is 135. So add it up. So you get 3 plus 2 is 5. So 855 is your final answer. Your maximum value. This is your maximum value, and this is your minimum value. You saw your maximum value occurred at 40, 15, minimum value at 15, 20. Maximum at 40, 15, minimum at 15, 20. Option C is your right answer. A very, very simple and straightforward question, my dears. You can very clearly see that this question is a straightforward question based on the corner points of an LPP. Next question, my dears. The number of corner points. So now the question is about how many corner points it has. So we know that a solution of an LPP requires you to draw the graph, obtain the feasible region, put it in the value of z, and find maximum or minimum. So they're dividing your questions for MCQ from each of these steps. Now you just need to just draw the graph here, my dears. X minus y equal to 0 is a straight line that passes through, no doubt, this straight line passes through x equal to 0, y equal to 0. Then the next point could be anywhere, like say 2, 2. Okay, so we just get to draw the direction of the line, that's all. Next one, 2y is equal to x plus 2. So if you try to plot points for this line, you can see that when x is equal to 0, y is equal to 1. If y is equal to 0, x is equal to minus 2. This is just to help me to draw the graph correctly without a mistake, my dears. So when I plot the graph, I can see that this is going to be my graph, all of you. Yes. So I'm drawing this as x-axis and the y-axis. The first point is 0, 0. Yes. And then it goes to 2, 2. My dears, I am only interested in the points on the axis. Just because I wanted to draw the line correctly, I found the point 2 comma 2. Actually, I'm not interested in those kind of lines. You will understand that when I start teaching you the original 3-mark questions for a line which passes through 0 comma 0. The next situation, my dears, the line which passes through 0 comma 1. 0 comma 1 and minus 2 comma 0. This is your second line, my dears. So the second line passes through, all of you, the second line passes through these 2 points, and I think it's passing through 2 comma 2 also. I'm not sure about that, but we will test the shading region, my dears. We know that this is line number 1 and this is line number 2. Line number 1 says that I have to find a region which is true for the line number 1. Line number 1 has 2 regions, and please remember this, my dears. Every straight line on an XY plane divides the XY plane into 2 half planes. Please keep this a very good question for an MCQ. A straight line divides my XY plane into 2 half planes. So which half plane is the correct region for the yellow line? So for that, we will test any point in that half plane. For this line, I will use the point 0 comma 1. Let's say we will use the point 0 comma 1 for this line. When I use it, I will get the equation is x minus y greater than or equal to 0, 0 minus 1 greater than or equal to 0. This is a false point. So this point is a false point, my dears. So 0 comma 1 is a false point for the yellow line. So we have to shade below the yellow line. I hope everybody understood why I'm shading below the yellow line, because 0 comma 1 is a false point for the yellow line. Now let's go for the white line, my dears. Let's go for the white line. Now this white line has a very easy point to check. We will put 0, 0 itself. 0, 0 is the most common point of testing. 0, 0 is the most common point we use for testing, but we cannot use 0, 0 for a line which passes through 0, 0. The first line passes through 0, 0, so please don't use it. That is the most common mistake I've seen students doing in finding the feasible region of an LPP. So please use 0, 0 only for those lines which does not pass through 0, 0. So 0, 0 implies this equation is 2y is less than or equal to x plus 2. So 0 less than or equal to 0 plus 2. So 0 less than or equal to 2 is a true condition. So for the second line, origin, shading towards the origin is a true condition. So let us shade towards the origin, okay? And we can see that our feasible region where both the red and the pink are coinciding is very beautifully expressed by this particular region, my dears. It's everywhere on this region. And this particular region is described by how many corner points? Check, my dears, this particular region is defined by 2 corner points only. You can see that there are only 2 points on this feasible region. There are no other points described over here. So we can clearly say that this feasible region is obtained using how many corner points? 2 corner points, that's all. This is just a step that we use in LPP. They're testing your ability to solve an LPP, nothing else, okay? Next question, my dears. The objective function z is equal to ax plus by has a maximum value 42 at 4, 6 and a minimum value 19 at 3, 2. Very simple. They're saying that z is equal to 42 at x equal to 4, y is equal to 6. Put it over there. Z is equal to ax plus by implies 42 is equal to 4a plus 6b. Now we can simplify it. Yes, goes into 2a plus 3b. Equation number 1. Next one, my dears. Z is equal to 19 at x equal to 3, y equal to 2. Substitute. Z is equal to ax plus by implies 19 is equal to 3a plus 2b. So there is nothing to solve here. So equation number 2. So solve the 2 equations, my dears. So solve the 2 equations to get the values of a and b, or you can just substitute and check. That is also your interest, that's all. my dears, equation number 2 is being multiplied with 3. When equation number 2 is multiplied with 3, 9 3s are 27, 9 3s are 27, 2, 3 1s are 357 is equal to 9a plus 6b. Equation number 1 is multiplied with 2, so you will get 42 is equal to 4a plus 6b. If you subtract, you will get 15 is equal to 5a, implies a is equal to 3. I got the value of a is equal to 3. There is only one option with a is equal to 3, and then definitely if a is equal to 3, I can conclude that b is equal to 5. That's all. Very simple idea, my dears. I just substituted the value of z, x and y. I got two equations of a and b. I just solved it. Very direct question, my dears. The corner points of the feasible region of an LPP are 0, 4, 8, 0, 20 by 3, 4 by 3. There are 3 corner points. Then you have to find out what is the maximum value of z minus the minimum value of z. Very similar question, my dears. We did question number 1 based on the same idea. So we'll just put 0, 4. The first corner point in z is equal to 30x plus 24y. So if you put that, you will get first value of z is equal to 0 plus 24 times 4, my dears. So it's going to be 96. So your answer is going to be z is equal to 96, the first value of z. Next corner point, my dears, 8, 0. So z is equal to 8 3s are 24, so 240 plus 0. So the final answer is 240. Next point, my dears, 20 by 3, 4 by 3. If you substitute 20 by 3, 4 by 3 in z, you will get 20 times 30 by 3, that is 200, plus 24 times 4 by 3, that is 32. So your answer is 232. So very clearly, the maximum value is, this is your maximum value and this is your minimum value. So we have to find maximum minus minimum, my dears. So maximum minus minimum is equal to 240 minus 96. 240 minus 96. So your answer is going to be 100 and 100. So it's going to be 10 and 6 is 4. So the final answer is 144. Yes. So we don't have a final answer in these options. I think it's a mistake on the question side. So we have to say that none of the options are right here. No options are correct. So you will get full marks in this question, obviously. No options are correct in this question. So you get a full mark in a question where no options are correct. Obviously, there's nothing mistake in the calculations that we did. So 0, 4 is always going to give me 96 over there. So 144 is not an option here. So obviously, you will get a full mark. Question. The feasible region of the linear programming problem is shown in the figure below. Which of the following are the possible constraints? First one, see x plus y. X plus y equal to 3 is this line, my dears. All of you please check this line. X plus y equal to 3 is your first line. And x plus 2y equal to 4 is the second line. In both the cases, we are shading towards the right side of the lines. Means 0, 0 is not a solution in the feasible region. Okay, so you check which condition says 0, 0 is always false. My dears, very clearly from the options that it is going to be option number C. Okay, option number C is the only situation where they keep the shading in the first quadrant and both the conditions say that it is greater than. Greater than means it is not going to be 0, 0. Check 0 plus 0 greater than 4. False. Origin is false. 0 plus 0 greater than 3. Origin is false. So the C option is the only option where 0, 0 does not lie in the feasible region. I hope everybody is clear. Yes, my dears. So that's the only way to do it, my dears. Okay. Very simple concept. Clear? So 0, 0 is not being included in the feasible region. So you decide based on that. All of you clear? Yes. Next question, my dears. The solution set of, again, it's just a single line. And I just now said in the introduction part, a linear inequality always divides my plane into two half planes. So 3x plus 5y less than 7. So we will say, let's check 0, 0. So 3 into 0 plus 5 into 0 less than 7. So 0 is less than 7 is true. So that is, origin is part of this feasible solution. Origin is part of this feasible region. So we know that a straight line divides it into two half planes. A linear inequality divides my LPP feasible region into two half planes. So one half plane towards the origin is true for this case. Whole XY plane, wrong. Whole XY plane, wrong. Open half plane containing the origin, possibility. Open half plane not containing the origin, false. So we saw that 0, 0 is a point in the feasible region. So it's a whole open half plane containing the origin. Okay. Then what do you mean by except the points of the line? Please have a very clear understanding on this. This inequality very clearly mentions that this is strictly less than 0. Strictly less than 0. When it is strictly less than 7, then it is not including the points on the line. It will include, my dears, check it this, my dears, 3x plus 5y less than or equal to 7 will include the points on the line. Will include the points on the line. So try to understand, my dears. They will always confuse you. Please try to understand this does not include the points on the line. Okay, fine. So this is going to be your answer, option C. Next question. Which of the following points satisfies both the equations? Just substitute and check, my dears. Don't waste your time too much. Just substitute. Option -2, 4. Let us put -2, 4 in the first equation. The first equation is going to be 2 into -2 plus 4. -2 is 0 less than equal to 10. It does include, correct. Next one, -2 plus 4 twos are 8. That is 6. It is false. So, this is not the answer. Let us try B, 3, 2. X equal to 3 makes it 6 plus 2 less than equal to 10. That is 8 is less than equal to 10. It's correct. Now 3, 2 in this one. 3 plus 4 greater than or equal to 8. 7 greater than or equal to 8. False. So this point is also wrong. Let's say option C. -10 plus 6 less than equal to 10. So it is -4 less than equal to 10 is correct. That is, I'm trying to do point C, -5, 6. Put that -5, 6 in the second one. -5 plus 12 greater than or equal to 8. -5 plus 12 is 7 is greater than or equal to 8. It's false. So -5, A6 is also wrong. Let's try 4, 2. Option D. 4, 2. So it is 8. First equation, 8 plus 2. 8 plus 2 less than equal to 10. That is 10 less than equal to 10. Less than or equal to. So it is true. Next point, my dears. X plus 2y. So 4 plus 4 greater than or equal to 8. That is 8 is greater than or equal to 8. That is also true. So the only option which is true for both the equations is 4, 2. So they're asking which point is suitable for both the regions, both the half planes. So they are putting the equal to sign also. So the option D is the right answer for us. Okay, just check the options. Okay, don't try to draw graph for this. It is impossible to do graph and then it's wastage of time. You simply put the points and check. The points are very clearly given to us. Okay, next question. The feasible region corresponding to the linear constraint of the linear programming problem is given below. Which of the following is not a constraint to the given linear programming problem? So very clearly we can see that for each line, understand what is happening. This line, let's say line number 1, it says I should go above the line. Let's say line number 2, this one. I should go towards the origin. Do you see that it is going towards the origin? Okay. And line number 3, this line also says, let us go towards the origin. So it is very clear that the feasible region obtained by the 3 lines in which only line number 1 says I should go away from the origin, but line number 2 and line number 3 says I have to shade towards the origin. Now the question is, which of the following is a true statement? That's all. First one, x plus y is greater than 2. It looks like line number 1, my dears. The first one, this looks like line number 1. So in x plus y greater than or equal to 2, substitute origin 0 greater than equal to 2 is false. Origin does not lie in x plus y. So equation number 1, look at that. Equation number 1 says origin should not be a part of it. Now you got an option A also, origin should not be a part of it. So 0, 0 does not belong to x plus y greater than or equal to 2. According to the option C, equation number 1, x plus y greater than or equal to 2. So they are asking you which of the following is not a constraint. So this is a constraint. So this is not the answer. X plus y greater than or equal to 2 is a true constraint for the inequality, for this feasible region, because this feasible region says I should shade everything above that. And 0, 0 is not a part of it. So I'm shading everything above it. So it is a constraint, not a constraint. Okay. All of you try with option B now. X plus y less x plus 2y. So this one says, okay, let's try with 0, 0 here. 0 plus 0 less than equal to 10 is true. So that constraint says shade towards the origin. So 0, 0 is a part of that constraint. 0, 0 is a part of that constraint. So this is also a constraint. Okay, they want not a constraint. Careful. They want not a constraint. Okay, x minus y greater than or equal to 1. Okay, let's try that. Let's try origin for that. 0 minus 0 greater than or equal to 1. 0 greater than or equal to 1 is false. So 0, 0 is not a part of this constraint. But the line which says x minus y equal to 1 says that 0, 0 is a part of that constraint. So obviously my answer is here. My dears, this is my right answer. Okay, this is my right answer, because this answer says that for this constraint 0, 0 is not a part of that region. But for this exact diagram, x minus y equal to 1 says that 0, 0 is a part of that feasible region. So all of you please note it. This is the constraint which is not a part of the feasible region over here. Okay, all of you clear? Just check which one doesn't satisfy 0, 0. Clear, my dears? So first line says 0, 0 is not a part of me. So we tried that inequality. That also said 0, 0 is not a part of it. Second constraint says 0, 0 is a part of it. So when we check the option, that also says that 0, 0 is a part of it. So it's correct. Third one says in the diagram 0, 0 is a part of that line, but in the option 0, 0 is not a part of that line. So I said that's the constraint which cannot be included in the feasible. It should have been this, my dears. This one is correct. Less than equal to 1. Where 0 is less than 1 is true. So that will be a part of that. So this is the correct form of the constraint. This is what they asked for case study also. Which of the following is true, which of the following is not true. That's it. You just got to find the correct one by putting what? 0, 0. And 0, 0 cannot be used for a constraint which passes through origin. Next question, my dears. The point which lies in the half plane. Again, substitute and check, my dears. Nothing else. Just substitute 0, 8. Option A, 0, 8. 8 is less than or equal to 4 is false. So which point lies in the half plane? So this does not lie. 1, 1, option B. So 2 into 1 is 2 plus 1 less than or equal to 4. So 3 is less than or equal to 4 is true. So which point lies in the half plane, 1, 1 lies in the half plane. Other points do not. Okay, very easy answer. The corner points of the bounded feasible region of an LPP. They are giving you the corner points. Very clearly, the corner point number 1 is 0, 0. A is 250, 0. B is 200, 50. And C, which is going to be 0, 175. All the corner points, 4 corner points are given to us. Z is equal to 2AX plus BY. Z is equal to 2AX plus BY occurs at the points 250, 0 and 250. Both the corner points gives me what? The maximum value of the objective function. That means Z at 250, 0 will be same as Z at 200, 50. Otherwise, 2 points cannot give you the same value for Z, right? So, substitute X and Y here. That implies 2A into 250 plus 0 equals 2A into 200 plus B into 50. So, we have 500A is equal to 400A plus 50B. So we have 100A is equal to 50B. So 2A equals B. That is the equation we got. 2A equals B, option A. Very simple and easy answer. The same question can be modified to a 5-mark or a case study based question where 2 points give me the same value for Z. You use the 2 points to get the relationship between the 2 values A and B. It may be A and B, P and Q, whatever it is. It's a very, very famous question. 2 corner points giving you the same value. Okay? Next question, my dears. A linear programming problem deals with the optimization of Z. We know that Z always looks like AX plus BY because we are using the solution in the method of graphicals. Yes? Graphical method is the method we are going to use to solve an LPP. A graphical method with XY plane in 2 variables, and our linear programming problem deals with the optimization of not logarithmic, not quadratic, not exponential, linear function. Please be careful. It's a one-word answer. LPP is always designed on linear equations. Because in 12th standard, we have only a graphical method by drawing straight lines to find out the solution of an LPP. So our LPP problem deals with the optimization of an objective function, which is also a linear function. Okay? We have linear constraints and we have linear functions. Clear? Linear constraints for drawing the graph and linear function to be optimized. Please be careful. Okay? Next one. The number of corner points of the feasible region determined by x greater than 0, y greater than 0. There is only one line we should be concerned about, x plus y greater than or equal to 4. And if you try to plot a graph for that as a straight line, we can see that if x equal to 0, y is 4. Y is equal to 0, x is 4. So now we have a straight line, my dears, which passes through 2 points, which is 0, 4 on y-axis, 4, 0 on x-axis. And if you try to draw a line for that, definitely this is the straight line. And our shading should remain in the first quadrant because the question says so. Y is positive, x is also positive, my dears. So we should stay in the first quadrant. Now we have to shade either towards the origin or away from the origin. So wherever we shade, obviously we'll try it actually. 0, 0 implies 0 plus 0 greater than 4. It is a false statement. So we cannot shade towards the origin. We have to shade away from the origin. Whatever be it, we definitely have how many corner points here? We have how many corner points? 2 corner points. So our answer is going to be, number of corner points is going to be 2, my dears. Very easy question can also be asked like this. Okay, and the chances of asking a complete LPP solution for MCQ is very rare, but they can ask. We've seen a question like that. Okay? Simple question, my dears. Next one. Read the options, my dears. It's a direct question. The common region determined by all the constraints together. I've been saying this word repeatedly today. Yes, the common, in this video, I've said this word so many times. The common region that is obtained by all the constraints is called a feasible region. What region, my dears? Feasible region. Don't confuse. Clear with the words. Corner points. Corner points are substituted in the objective function called z, which is a linear function. And the linear function will provide us a maximum value or a minimum value, which is called the optimal solution. Optimal. See, the technical words are very important. My dears, once again, listen very carefully. We have linear constraints called inequalities to draw the graph. And drawing the graph and then shading the region called the feasible region. Region is called what? Feasible region. And the feasible region will give us corner points. Corner points are substituted in the objective function, which is a linear function. Objective function z, which is a linear function. From the linear function, we get maximum value or minimum value, and both of which are called as the optimal solution. Optimal solution. So here, we want the name of the region. It's called the feasible region. Clear? Terminologies are important. Very important, straightforward questions. Next question, my dears. The restrictions imposed on the decision variables involved in an objective function of a linear programming. Restrictions. Restrictions means we are calling it as constraints. Correct? What restrictions are we imposing on the objective function? We are substituting the corner points in the objective function. Corner points are given by the feasible region. Feasible region is obtained by what? The constraints. So, what restricts the objective function's value? The feasible region. Feasible region is obtained by what? Feasible region is obtained by what? The constraint. So, what imposes the restrictions on our LPP problem, my dears? Constraints. So, next question, my dears. Of the following, which group of constraints represents? See, before we did a question with 3 lines. Now we are doing a question with only 2 lines. Now, my dears, look at this, my dears. Line number 1, let's say this is line number 1. Line number 1 says, shade everything above me. That is where the shading is staying above that line. Okay? Line number 2, my dears. Line number 2 over here. This says, shade everything below me. That is why it is shaded on this. See, the region which coincides for both red and the pink shading is the region that is shaded over there, right? So we'll check what condition is going to be true for this. Okay? All of you, check the option number 1. X plus 2y is equal to 76 is equation number 1. Equation number 1 says shade everything above me. Above means it is not less than. See, what happens if you put for less than? If x plus 2y is less than or equal to 76, 0, 0 implies 0 is less than 76 is a true case. That means origin is a part of that region. Wrong answer. So this should not be the right one. So I want the right answer to be x plus 2y greater than or equal to 76 because origin should not be a part of it. The option which says, so we have 2 cases here, my dears. Both these cases say that is greater than, but the second one says, I want 0, 0 to be a part of it. What is second one? So 2x plus y less than or equal to 104. To make 0, 0 a part of it, I have to put less than. So if you put 0, 0 here, 0 less than 104 becomes a true case. So I want the case which says this is greater than and this is less than. Which one, my dears? Greater than for 76, less than for 104. That is option C. Greater than for 76, less than for 2. Just check which region is going to be suitable for that. And then shade it, that's all. See, they are technically asking you what you normally do in a 3-mark question. So if you know the procedure for a 3-mark question properly, these are very easy questions to do, my dears. Okay? Next one. The maximum value of z occurs at what point? Just substitute, my dears. Yes, and then find out what is the maximum value. Here we have how many corner points? Just check. 0, 0, 30, 0, 20, 30, 0, 50. Just substitute each of the points. 0, 0, 30, 0, 20, 30, 0, 50. And we will put in our z, which is 4x plus y. First value 0. Second value 120. Third value 80 plus 30, 110. Fourth value 50. So the maximum value is what they want, which is 120. 120 is option C. Finished. The last step in an LPP solution, just finding what is the maximum value of this feasible region. Okay. Next, assertion reason question came, my dears. The corner points of the bounded feasible region of a LPP are shown below. The maximum value of z is equal to x plus 2y occurs at infinite points. I already explained to you when does the feasible solution occur at infinite points. When there are two corner points giving the same maximum value. Find out what are the corner points here, my dears. All of them are given to us. The first one, P, is 60, 0. Okay. Q, which is 120, 0. R, which is 60, 30. And S, which is 40, 20. Find out the values of Z, which is equal to x plus 2y. The values of Z, my dears, the first one 60, second one 120, third one 60 plus 60, again 120, the fourth one 40 plus 40, it's only 80. So we saw that the maximum value occurs at 2 points. Yes, Q and R. If maximum value occurs at 2 points or minimum value occurs at 2 points, whichever be the question, here the question is about maximum value. If the question was about minimum value, it is occurring at 1 point, 60, finished, over. One single solution, answer is done. But when they ask you about maximum value for this question, you saw that it occurs at 2 points. If it occurs at 2 points, and what are the 2 points? I'm going to explain to you very carefully, listen, Q and R. The two maximum values are at Q and R, then definitely your solution will occur at all the infinite points starting from here to here. On this complete line, there are infinite points on this line, so you will get your solution all these infinite points. So my dears, this is a true case, my dears. Listen, this is a true case. Okay, so we will say that our answer is assertion is true. Now let's check the reason. The optimal solution of a LPP having bounded feasible region must occur at corner points. My dears, the optimal solution of a LPP having a bounded feasible region must occur at corner points. That is false. Because the optimal solution here was at Q and R, but we said that Q and R are not the only solutions. It is on all the infinite points. So this is not a true statement. So your A is true, R is false. So your answer is option C. It is not necessary that for a bounded feasible region, the optimal solution must occur at the corner points. In the case where there are infinite solutions, the optimal solution can occur, okay, at corner points, but also at other points, other infinite points on the line. Okay, clear, my dears? So moving on. So the answer is option C. A is true and R is false. So with this, I think we have concluded with the 1 mark questions in assertion reason. Only one question came throughout this. So let's continue with the MCQ now. For the linear programming problem, Z is equal to 4x plus 3y and the feasible region determined by a set of constraints shown in the graph. Which of the following statements is true? They are talking about maximum value, minimum value at all corner points. So let's try to find out the values. That is it. Z is equal to 4x plus 3y. Okay. Then what are the points? 0, 40, 30, 20, 40, 0, 0, 0. Substitute. The first one is going to be 120. Second one is going to be 120 plus 60, 180. Next one is going to be 44s are 160, and next one is going to be 0. So my dears, maximum value is at 40. False. Maximum value is at 3020. True. Value of Z at R is less than at P. At R is less than. That's false. The value of Z at Q is less than. No, that's not possible because that's the maximum value. So option B is the right answer. Maximum value of Z is at Q 3020. Yes, very simple answer based on the value of Z. So many questions based on value of Z, my dears. Yes, next one. Read this question. A linear programming problem along with the graph of its constraint is shown below. The corresponding objective function Z is equal to 18 plus 10y, which has to be minimized. The smallest value of the objective function is 134 and is obtained at the corner point 3,8. Smallest value is obtained at 3,8. Okay, next. The optimal solution of the above linear programming problem does not exist as a feasible region is unbounded. My dears, unbounded solution. Very good theory to learn. See, my dears, once you get a minimization problem, okay, carefully listen, a minimization problem which is unbounded. A minimization problem unbounded always requires you to check one more additional question. See, they said the minimum value is 134. So we will draw the constraint Z less than 134. Draw a new constraint. After the complete solution, draw a new constraint for Z less than 134. That is 18x plus 10y less than 134. Okay? In a LPB problem, we will do it. But right now, listen. The line is already drawn for you. Please, can you see this? All of you, I'll show this very clearly over here. That line is already drawn for you. Can you see this line over here? It is not properly visible, then please see this. I'm drawing it a second time. This dotted line is already drawn for you. Okay? Do you see that line, my dears? Yes, 18x plus 10y equal to 134. A dotted line is drawn, my dears, over there. Now, do you see that this dotted line does not pass through the feasible region? All of you, please. Our feasible region is here. Check it out. Our feasible region is occurring in this part. This is the place where we get our feasible region. It's properly shaded for us. And the shading for the new constraint is towards this side. Do you see it? They have shaded it for us. It is towards this side. So you can see that these two are not overlapping. Okay? Or in simple words, this dotted line does not pass through the feasible region. If it does not pass through the feasible region, we can always confirm that Z is equal to 134 will be the optimal solution. Will be the optimal solution for this LPP. My dears, once again, for an unbounded solution, minimization problem, maximization problem is different. Minimization problem, unbounded, when they ask you, you have to always check this new constraint. Constraint which says the objective function Z, which is less than your optimal solution that you got. If that straight line passes through the feasible region, you can immediately decide that the solution that you got is not the optimal solution and you cannot find the optimal solution using graphical method. But if it does not pass through the feasible region, you can immediately conclude that the solution that you got is optimal and 134 will be the optimal solution. So here option A is wrong because it says that does not exist as the feasible region is unbounded. It does exist. B, does not exist. Wrong answer. Exists as the inequality 18x plus 10y greater than 134. Wrong option. Greater than is the wrong option. Less than is what we want. Exists as the inequality 18x plus 10y less than 134 does not have any point in common with the feasible region. That is your answer. Got it, my dears? A very, very simple unbounded technique. This is a verification technique for an unbounded solution for a minimization problem. Okay, don't write for maximization. Okay, next one. Okay, now we can go to the 5-mark questions. So in this video, like I said, after 1 mark, I'll be discussing the 5-mark questions which came. Only 2-3 questions are there throughout the regions, my dears. A very simple, straightforward LPP. Okay, my dears. First question, solve the following linear programming problem graphically. Maximization problem with only 2 constraints, my dears. They are also 5 mark. Okay, so same thing we did for 1 mark MCQ also. Okay, my dears, the first equation. So I have a logic of calling it equation number 1. Okay, let us try to find the points for drawing the graph. X is equal to 0, y is equal to 9 by 2. Y is equal to 0, x is equal to 3. I got the first points, which is 0, 9 by 2 and 3, 0. Second one, my dears, equation number 2. 3x plus y less than or equal to 9. X and y, points to be plotted. X is equal to 0, y is equal to 9. Y is equal to 0, x is equal to 3. So the corner points are 0, 9 and 3, 0. I got the corner points for equation number 1 and corner points for equation number 2. Now let us draw it, my dears. All of you, drawing the graph over here. Not going to be very accurate with the graph because it's only 2 lines. Okay, I just need to get the region correctly. So, but when the exam comes, please, my dears, make sure you are a bit accurate for it, but be sensible in marking the points on the axis. Don't put always 1, 2, 3. For big numbers, you can put 2, 4, 6, 3, 6, 9. That's your choice. 5, 10, 15. Please make sure that the graph fits the page. Okay, so don't draw too much like small coordinates for a big number. Okay, now here it's all up to 9 and all. So we will take the points as 2, 4, 6, 8, 10. Here, I'll go with only 1, 2, 3 because the biggest number is. So 1, 2, 1, 2, 3, 4, 5. Okay, now 0, 9 by 2. 0, 9 by 2 means 0, 4.5. That is somewhere over here. The first point, 0, 9 by 2, 4.5. Up to 3, 0. 3, 0. So I got my first line, my dears. My first line is from here to here. And I will call it as equation number 1. I already named it. It's useful for us in drawing the diagram. Equation number 1. 0, 9. Second line is made from 0, 9, my dears. 0, 9. And it goes to 3, 0. Again, 3, 0 is already there with us. So we will draw the line from 0, 9 to 3, 0. Okay. And we will call it as equation number 2. Now we are trying to shade it, my dears. We know how to shade it, right? Test with the origin. So all of you, if I put 0, 0 in this case, 0, 0 implies 0 is less than 9. So the first equation says shade towards origin. Next one, 0, 0. For this one implies 0 is again less than equal to 9, which is true for the second line as well. So for the first line also, I need towards the origin. Please, my dears, stay towards the origin. And for the second line also, stay towards the origin. So we are going to shade only this part, my dears. The region where it's going to coincide for both the cases. So this is so please in the exam, you shade properly the required feasible region. The other shadings are not at all compulsory or mandatory to show. It's just to understand only you mark them. Okay. And I got my corner points for this feasible region. That is 3 corner points. And I know all the 3 corner points here, my dears. A, B, C. I know all the 3, my dears. So I'm going to put it over here. A is going to be 0, 0. B is going to be 3, 0. And C is going to be 0, 9 by 2. And that will be substituted in my objective function. So what is the value of z in the first case? Z is equal to 70x plus 40y. 0, 0 means it is 0. 3, 0 means it is 210. 0, 9 by 2 means it is 20. It's 180. So the maximum value is what I want. The maximum value occurs at, so you will write this as your answer. Maximum Z is equal to 210 at B 3, 0. Therefore, optimal solution is Z is equal to 210 at x equal to 3, y equal to 0. That's it. Write the solution, a single solution. It's a 5-mark question, very easy for us, for a 5-mark, my dears. It came in 2023, a 5-mark question, my dears. Next one, my dears. Solve the following LPP, again for a 5-mark in 2023 with only 2 constraints. So let us find the solution here, my dears. Equation number 1 says 3x plus 4y greater than or equal to 8. Again, plot the points. X equal to 0, y is equal to 2. Y is equal to 0, x is equal to 8 by 3. So my first point is 0, 2 and my second point is 8 by 3, 0. Equation number 2, my dears. Equation number 2 is 5x plus 2y greater than or equal to 11. Again, plot the points. X is equal to 0, y is equal to 11 by 2. Y is equal to 0, x is equal to 11 by 5. So my next points are 0, 11 by 2 and 11 by 5, 0. Okay, just they're giving you fractional values for the coordinates, that's all. So now let us try to draw the graph. Plotting the points and drawing the graph, my dears. Okay, now we can see that the y values go up to 11 by 2. 11 by 2 is 5.5. So we can say this is 0, 1, 2, 3, 4, 5 and 6. And the x value maximum is 11 by 5 is 2.5, 2.2 something, and 8 by 3 is again 2 point something. So the biggest value of x is 2 point something. So 1, 2 and 3. Okay, so the first coordinate is 0, 2, 8 by 3, 0. 0, 2, my dears. 0, 2 is a point on y-axis. And 8 by 3, 0. 8 by 3, it's 2 point something. So it's somewhere over here, 8 by 3. 8 by 3 is somewhere over here. So 8 by 3, 0. I got the first line, all of you. The first line is drawn from 0, 2 to 8 by 3, 0. So, okay, I'll call this as equation number 1. Okay, second one, my dears, 0, 11 by 2. 0, 11 by 2 in the meaning that 0, 11 by 2. 11 by 2 is 5.5. Okay, next one, 11 by 5. 11 by 5 is 2 point something. So 11 by 5 is 2 point something somewhere over here. So it's going to be this one, my dears, 11 by 5, 0. Draw the line for that, my dears. The line for that is going to be equation number 2. Now we shade the region, my dears, which by trying what is 0, 0. Again, all of you, if I put 0, 0 in this, if I put 0, 0 in this, I get 0 greater than or equal to 8 is false. Origin is false here. If I put 0, 0 in this, 0 is greater than or equal to 11, that is also false. So it is very clear that I have to shade for both the lines away from the origin. So this is how the shading for the first line goes. Yes. And the shading for the second line, my dears, away from the origin. So pretty clear that my shading is in this region. All of you, please understand, my shading is restricted in this region, all of you. here. And we are getting an unbounded solution. In the MCQ discussion, I clearly told you what the unbounded solution is. An unbounded solution should always be verified by one extra condition. This is unbounded, all of you, but we'll still find the corner points, no doubt. First corner point, second corner point, and third corner point. And we will call them by the name A, B, and C. There is only one corner point I have to find, that is called B. How to find B? So we'll solve the two equations to find B. To find B. I'll solve the two equations, my dears. Equation number 1, so equation number 2, I'll multiply with 2. I will get 10x plus 4y is equal to 22. Just a system of equations, so simply solve the method by elimination. Okay, so 3x plus 4y is equal to 8. You subtract it, you will get 7x is equal to 22 minus 8, which is 14. So x is equal to 2. B coordinate x is equal to 2. Now go for y, all of you. 5x plus 2y is equal to 11. So 5 2s are 10. So 2y is equal to 11 minus 10. Y is equal to 1 by 2. So I got the value of B, which is 2 comma 1 by 2. Okay. Now we will find out the optimal solution, the value of Z for these three corner points. We will do verification after that. A is equal to 0 comma 11 by 2. B is equal to 2 comma 1 by 2. And C is equal to 8 by 3 comma 0. I have the three corner points now. And what is my value of Z? Value of Z is minimize 60x plus 80y. 60x plus 80y. Substitute 11 by 2, that is 40 into 11, which is 440. Now 2 and 1 by 2, so 2 makes 120, 1 by 2 makes it 40. So 40 and 120, it is 160. Now 8 by 3, so 60 by 3 is 20, so 8 2s are 16, 160. Again, you have multiple solutions. 160, multiple solutions. Minimum value occurs at both B and C. Minimum value occurs at both B and C, which is 160. So we will see all the infinite solutions. That is the first thing. Second thing, it's unbounded. So we will say it's unbounded. Feasible region is unbounded. Therefore, Z less than 160. We are verifying if there is any value for Z which is less than 160. From the equation we know Z is 60 plus 80. So 60x plus 80y less than 160. It goes in 20, my dears. 3x plus 4y less than 8. Yes, 3x plus 4y. So we will draw an inequality for this. Yes, we will draw an inequality for this, my dears. Let us try it out. If x is equal to 0, y is equal to 2. If y is equal to 0, x is equal to 8 by 3. So we have to draw a dotted line between 0, 2 and 8 by 3, 0. 0, 2 and 8 by 3, 0. Where is 0, 2 and 8 by 3, 0? A dotted line between that. So the dotted line that goes between 0, 2 and 8 by 3, 0 is definitely this line itself. You can see, all of you, it is this line itself that is going between 0, 2 and 8 by 3, 0. And does this line by any chance, my dears, does this line by any chance pass through our feasible region? No. It does not pass through the feasible region. So we will conclude that Z less than 160, that is 60x plus 80y less than 160, does not have any common region or point in the feasible region of the LPP. Feasible region of the LPP. We can very clearly see that this unbounded solution does not have any feasible region with this inequality we just now constructed. So we'll conclude that therefore z is equal to 160 is the minimum value. That is our minimum value. Obviously, that is our minimum value. But it occurs that at all infinite points on the line, containing B. What is B, my dears? 2.5, 8 by 3 and 0. 2.5 and C 8 by 3 comma 0. My dears, normally it would have been just 1 point, but this is a 5-mark question. They did two things over here. One is multiple solution. Second one is unbounded solution. Multiple solution because 2 points have the same minimum value. So the answer is at all infinite points. But since it's unbounded, we have to verify this also. Verifying that the line that we have drawn now does not pass through our feasible region. It just stays outside our feasible region. See that? The dotted line just stays outside our feasible region. Please learn this unbounded solution technique. It's a very good question to be asked. Okay, my dears? Next question, all of you. Maximize z is equal to, here we have three inequalities. Careful, all of you. Three inequalities. Equation number 1 implies x plus 2y less than or equal to 12. X plus 2y less than or equal to 12. So we'll draw the constraints, all of you. X and y. X equal to 0, y is equal to 6. Y is equal to 0, x is equal to 12. Equation number 2, all of you. 2x plus y less than or equal to 12. So again, x equal to 0, y is equal to 12. Y is equal to 0, x is equal to 6. So this is made by corner points 0, 6, 12, 0. This is made by corner points 0, 12 and 6, 0. Now the third equation, my dears, equation number 3 says 4x plus 5y greater than or equal to 20. Draw the line for that. So you have x, y. If x equal to 0, y equal to 4. Y is equal to 0, x is equal to 5. So the points are 0, 4 and 5, 0. So we got the corner points for all the three lines. So we will fix this on a graph now. And we know the graph is going up to 12 and all. So when you draw it, don't draw with always like 1 point. We can draw with 2 points also. A graph with 2 points. Okay. So I'll plot the points here. Starting from 0, 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. First point starting from 0, 6 to 12, 0. 0, 6, my dears. 0, 6 over here and 12, 0 over here. So 0, 6, please mark it. 0, 6 and 12, 0. Draw the line for that, all of you. I use this yellow line itself, 0, 6 to 12, 0. And I will call this as equation number 1. Okay. Equation number 2, 0, 12 to 6, 0. So 0, 12 to 6, 0. 0, 12 over here. 0, 12 to 6, 0 over here. Now we will draw a line for that. 0, 12 to 6, 0. Okay, equation number 2. Equation number 3, all of you, from 0, 4 to 50. 0, 4 to 50. 0, 4 over here. 50 over here. 0, 4 to 50. Drawing the line for that now. 0, 4 to 50. Okay. Now that's my equation number 3. So I have 3 equations with me. So I've marked all the 3 equations. Okay. Now finding the feasible region. We know we have to test with origin, right? Always test with origin. So this one says origin is true. My dears, I'm not verifying it always. 0, 0 less than 12. Correct. 0, 0 less than 12. Correct. 0, 0 greater than 12. False. For the first line, it's true. Second line, it's true. But for the third line, it's false. So check it out, my dears. First line says shade towards the origin. Yes. Second line says also shade towards the origin. Third line says shade away from the origin. So very clearly you can see that my shaded region over here is this region, my dears. This particular region is my shaded region. Only do that properly, my dears. In the exam also, show that region very clearly. Others can be shown very lightly with a pencil. Very lightly you put that arrow with the pencil and find which region is suitable for all the 3 constraints. And once that is obtained, mark the corner points. Number 1, number 2, number 3, number 4 and number 5, my dears. 5 corner points. We know number 1, we know number 2, we know number 3. We don't know D, we know E. So we are having only one corner point unknown to us, that is D. And D is formed by the combination of the green line, equation number 2, and the yellow line, equation number 1. So I am concerned about equations 1 and 2 to get the D. Not 3, 1 and 2. So from 1 and 2, all of you, from 1 and 2, we will find the unknown point called D. We will find the unknown point called D from 1 and 2. So what I'll do is, I'll multiply equation number 2 with 2. I will get 4x plus 2y equals 24. Equation number 1 implies x plus 2y is equal to 12. You subtract them, you will get 3x is equal to 12, x is equal to 4. Okay, now we go for y now. Put in a new equation. Equation number 2 implies y is equal to 12 minus 2x. That is equal to 12 minus 8. That is also 4. Therefore, D is equal to 4, 4. Please, my dears, some of you might try to find the point directly from the graph itself. I wouldn't advise that. Sometimes there might be a minute difference in the coordinates. It won't be an exact value from the graph. So please always solve and get the points. It's a request, all of you please solve and get the points. The unknown point D is also obtained. Now we can put these corner points in the value of Z. So what is the value of Z now? We put the corner points A, B, C, D, E. D we just now found out 4, 4. Now what is A? A is 0, 4, B is 6, 0. 0, 4, B is 6, 0. Next, C is point C is over here, which is that is 6, 0. B is 5, 0. Okay. This is 5, 0. This is 6, 0. Okay, good. Now fine. 5, 0, 6, 0. E is 0, 6. E is 0, 6. And this should be put in the objective function Z. Maximize Z is equal to 60x plus 40y. 60x plus 40y. You put it over here, you get 160. This you put 300 and this you put 360, and this you would get 240 plus 160, which is again 400. Then last one 240. I want the maximum value, which is z, equal to 400. Therefore, maximum z is equal to 400 at B 4, 4. Therefore, optimal solution is, what is the technical word, my dears? Optimal solution. Z is equal to 400 at x is equal to 4, y is equal to 4. That's the final answer. So I hope everybody is clear with these concepts. Yes? Okay. So then we will have one last question to discuss in this video. That is a case-based question that came in this topic from the LPP, which came last year. One case-based question. They're explaining so much about the case, but it's not difficult. You can very clearly see that it's based on an unbounded solution. All of you please read it. Based on this case, they have shown how the graph is going to look like. You don't have to plot the graph. It's given to you. The complete story is explained. The graph is given to you. You just got to answer the question. So we'll move on to the questions, my dears. Look at this. On basis of the above information, answer the following questions. Identify and write all the constraints which determine the given feasible region. Very simple, my dears. How many lines we have here? Line number 1, which is 3x plus y. Okay? And you can see that this line 3x plus y, line number 1, talks about anything greater than 0. So it's going to be greater than or equal to 8. That's all. You can see that origin is not part of that line. So 3x plus y is greater than or equal to 8. Now line number 2, let's go for this one. Line number 2. Okay, that says x plus y, and that line also says stay above it, so greater than or equal to 6. Line number 3, my dears, this one, x plus 2y, even that line says origin is not a part of it. So for all the 3 lines together, it's shaded. Dotted line is because of the unbounded solution. We have seen how to draw dotted line for the unbounded solution. Okay, so we saw that my first question is just to identify the correct inequalities for the constraints. Identify and write all the constraints, determine the feasible region given in figure 2. Done. I have written all the constraints. How did I decide everything is going to be greater than or equal to? Because none of the lines want origin as a part of it. All of them are half planes where origin is not a part of it. Question number 2. If the objective function is to minimize, find the values of x and y at which the cost is minimum. My dears, we can see that this dotted line does not pass through the feasible region. Okay, the dotted line does not have anything common with the feasible region. So the solution that we get from the corner points is your optimal solution. The solution that you obtain from the corner points is your optimal solution. They want the minimum of that. All of you, let us try to find out the minimum of each of them. The corner points are A 10, 0, B 2, 4, C 1, 5, and D, which is 0, 8. Okay, I'll put C also here. C 1, 5. D 0, 8. Now, my dears, put this in Z. The first value of Z is equal to 10 would make it 160, 2 would make it 32 plus 80, 32 plus 80, 112, and then 16 plus 100, 116, okay, and then 0 plus 160. I want the minimum value. Obviously, minimum value is this one. So that will be my optimal solution, because though it's unbounded, this is my optimal solution because that constraint, the dotted line, doesn't pass through the feasible region. So if the objective function is to minimize, find the values of x and y. Therefore, x equal to 2, y equal to 4, minimum z is equal to 112. So the minimum value is obtained at x equal to 2 and y equal to 4 with z value 112. Find minimum cost, assuming that the minimum cost is possible for this given. It's possible, they themselves said it, but we verified it because dotted line doesn't pass through the feasible region. Next question. So I think with this, yes, only 2 questions are there in this, okay? So get full 4 marks from this, just 2 questions, my dears. So then after this, I'll be coming back with section C, 3 mark question, the next part of the video. And I will not be discussing all the PYQs, my dears, because it's a repeated question. Again, so many questions came. It's all just repeated. You can just watch only the selected questions of 3 marks coming in the next video, my dears. Till then, that's it. Bye.